My friend said you were a bad man.
All right, good morning. So today we are going to continue our discussion on finish our discussion on branch prediction and how does branch prediction impact on influence your code performance. And but before we start, it's always, and also later on we are going to talk about data hazard and the approach that modern processors would take to address data hazard. But before we start, it's always a good idea to remind us where we were. So we said that for modern processor, pipelining is a very important concept in a way that now every processor is kind of like a pipeline processor that a centralized clock signal controls the operation of all components, and each operations are synchronized with that clock signal in a way that it means that whenever the component receives the clock signal, every component will start working and puts its intermediate result to something like a pipeline register or some kind of a register temporary storage, so that the temporary storage would be able to supply the input data or the control signal for the next part of the task. So that's the whole idea of pipelining. And the good thing about pipelining is that every unit on the processor can all act simultaneously when we are on different instructions. So you can maximize your throughput. So in a way, if you look at the pipeline diagram that we draw, although in the very beginning it looks like we are not fully utilize the processor, but when you start to fill every component with instructions, then at some point you will figure out that every cycle you are completing an instruction and your CPI is equivalent to 1 if the pipeline works perfectly. However, having pipeline working perfectly is not easy because you have to deal with 3 different types of hazards. So the first type of hazard is structural hazard. Means that sometimes we want simultaneous instructions, but because there are some conflicts in the resource, so we cannot support that. So to deal with that, we can definitely stall, we can definitely insert no up instructions. However, that's not efficient. So the best way to address that is definitely to modify the structure, or say the hardware structure, the architecture, microarchitecture of your processor. And the second type of hazard is called control hazard. And it's called control hazard because there are instructions like branches or function code instructions, or even exceptions could change the direction of your program execution. So, and there are chances that we have no idea what's the next instruction to fetch. So we cannot continuously fetch instructions like what we expect to do in a pipeline. So that's what we call by control hazard. And previously we have been talking about, except for stalls, you can, besides stalls, you can also use dynamic branch predictions. And we have been talking about quite a few dynamic branch prediction mechanisms to help on that. And finally, today we are going to touch base on the data hazard. Is the case when an instruction, a later instruction, is depending on the result of an earlier instruction. So again, right, we said that we have an assignment saying that asking you to how to draw a pipeline diagram, and here are the highlights of how to do it. And if you really have no idea how to do that, and if you need more examples, I encourage you to review the undergrad material. And I have a link here, which is the undergrad class that I taught in UC San Diego. So, and also for, we have a summarization about how to address those hazards, right? And for control hazard, we have been talking about the bimodal local predictor. We have about the global predictor. We have talked about, for global predictor, we have an issue that we cannot distinguish the pattern for different branches. So we add an exclusive OR as to the aliasing the conflict of global history with different branches. So that's called G-share. And then we have a tournament predictor, which saying that sometimes we want the benefit from global predictor. Sometimes we think local predictor will work well. And the tournament predictor is basically adding another layer of prediction in a way that we, in addition to the global or local predictor, we have a predictor to predict which predictor would work better for branch prediction. There are so many predicts here, but that's the tournament predictor. And TAGE is another idea of advanced dynamic branch prediction. As we mentioned, that some of the branches we need longer patterns, some of the branches we need shorter patterns. So the basic idea of TAGE is that we have a table of different histories, and for different branch we have different types of we will find out like the best lengths for each branch. So that's a basic idea of TAGE. And finally, the most recent advance of silicon technology allow us to build a large predictor. So the idea of perceptron is finally perceptrons, or say NM predictors, is finally making inroads into modern processors. So the basic idea of NM predictor is that we treat the history the branch history as the input, and we train the weights for each bit of the branch history, and the sum the linear algebra result of such a combination of weights and bits will be our prediction result. So in this way, if we find some of the bit history is actually a noise when we are predicting a branch, we can ignore that. So based on, well, but no matter what kind of branch predictor, the whole idea is that we want to make branch prediction as perfect as possible. So given that we have modern predictors, given that you have learned quite a lot programming techniques, and you know quite a lot architectural ideas, the last lecture we stopped at the question that which implementation would give you the best performance. So, but apparently, a lot of you didn't think about that, and a majority of you think about is either C or B, right? But actually, the best performing one is D. So now, for the first part of this lecture, we are going to tell you why D is the best performing one. But before we start, well, so that's our scoring for the last one. And you see, we have teams that are catching up. So you guys are definitely having a chance at the end. So today we are going to talk about branch prediction and the performance. We are going to talk about data hazard. If we have time, we are going to talk about Tomasulo algorithm. So now the first question that I would like to invite you to think is that we know a lot of you know that B is better than A. So as a warm up, why don't you go ahead and tell me the reason why B is better than A? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I would invite you guys to go ahead and have a group discussion. 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now I think it's a time to pick a team to let us know. What do you guys think? Okay, Rocket Team. Who is the scriber of you guys today? Okay, so Rocket Team, I saw a message saying that you guys passed. So Byung, I remember you are Team Valor, right?
No, it's instinct, the first one.
Okay, so what do you guys think?
So we think the first and third are correct.
The first and the third correct. So how do you tell that?
Yeah. So basically, the dynamic instruction count B will be having less because this while condition will be checked fewer times, one-fourth time
Mm-hmm.
basically than the
Mm-hmm.
first case. So we'll be
Mm-hmm.
having less dynamic instructions. And the third
Mm-hmm.
one is correct because yeah, because fewer branch instructions than A. Because this while will
Okay.
create a branch. Yeah.
So how about 2 and 4?
Okay. So the second one is incorrect because basically, if we have, we will be having same misprediction rate, basically same misprediction count for both the cases, but number of basically branch instructions would be lesser for B, which means basically the denominator, when we calculate the misprediction rate, the denominator, that is overall branch instructions, would be lesser for the B part.
Mm-hmm.
So
Mm-hmm.
yes, so basically we can say B will have higher misprediction rate than A.
Okay. Okay.
Yes,
And for 4, you can incur fewer
same
data
amount.
memory access.
Yeah,
Is that
basically they
true?
will have same. No, they will have same amount of memory, data memory accesses.
Okay. So what kind of data memory access do we have here?
So basically, I think C and X will be fetched once,
Okay,
and
so that's a pretty interesting question, right? So okay, so if we don't have sufficient amount of registers, then we would definitely put C and X in memory. So if you have a stack machine like Java, C and X, they will be in the memory. However, for let's say like RISC-V or x86, it's very likely that C and X, they will be in a register. So there is not actually any data memory
hmm,
accesses in this pieces of
right.
code. All right. So for so first of all, right, let's went through the okay. So thanks a lot, and I think you guys are giving me very good answers. And so first of all, why is B better than A? Right. So if you look at the compiled code, and this is in RISC-V, and for the A version, for each iteration, we will saying that if we have n iterations that we have to go, then we will have 4 times of four instructions per iteration. So if we have n iterations, then we will have 4 n instructions. And however, for B, although for each iteration we combine the instruction from 4 iterations, however, we only need 1 branch instructions every 4 iterations. So it turns out that on average, you will have 30 instructions per iteration, but you only need n over 4 iterations. So it will be 325 times n instructions in RISC-V implementation. So, and if you have some further optimizations, which you will learn later in when we are handling the data hazard, you will figure out that if we can arrange instructions like this, then we will further reduce the amount of data dependencies. So the performance will be a lot better in this way. And the other thing is because now we only have 1 branch instruction every 4 iterations. So the amount of branch instructions is definitely fewer than A. However, for the second answer, B has significantly lower branch misprediction rate than A. This is, I mean, so if we run it, you will figure out that this one is also true, but that's not easy to tell. So let me share this with you. So this is on an x86 processor. So if you use the perf program, which we have been talking about, you will figure out that for A version, we have a total of 2% of branch misprediction. And for the B version, we only have 36% of branch prediction. And my hunch is probably this, because um, if you think about the, and so I don't have a standard answer for this one, but I do believe this is probably like processor microprocessor dependent, in a way that if you think about that, if you have a branch predictor that's based on history, and if your history pattern like this pop count, the history is about like the worst case scenario, we need 64-bit history to capture the pattern for the wild X, and this pattern is pretty chaotic, so it's pretty hard, difficult to detect which bit we might exit from the loop. However, for B, because we only need probably like 16 bits of patterns to capture, plus it's very likely that you are going to exit your number somewhere at the very end of I would say, like, very likely you are going to finish your branch at like the 16th or the 15th iteration. So it's easier to capture that pattern in this way. So that's why for B, it's also true in a processor we tested, but I won't list it as a standard answer here, because this is very architecture dependent, right? So, but in general, and without the information about what kind of predictor that we are using, it's hard to tell if the second one is going to be true or false. But one thing I can tell you is that in modern x86 processor that use history prediction, is very likely the second one is also true. So, but I put answer C here because I think it's obvious, it's intuitive, or say it's very reasonable that 1 and 3, they are generally correct. Okay, so now the second thing I want you to think. We all agree that B is better than A, but one thing that we also found that C is better than B. So why? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like for this question, we also need some kind of discussion. So why don't we go ahead and discuss? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, I see a majority of B now. So you only think there's one thing right. So let's pick a team to tell me what's the one thing right that you guys thought. Okay, Valor. What's the one thing right that you guys thought? Woohoo, somebody home? Somebody home? Okay, so that's open to the public. Okay, Winston, you guys are really fast.
Yeah, I'm out here to win.
Hey,
All right.
so what do you think?
So I think I also thought it was B. Someone else thought in our group. I just want to say he also thought it was. I think C. He thought it was two of the choices. But I personally think it was. It has a lower dynamic instruction count than B. But one of my peers said it was also 4 as well. C can incur fewer data memory accesses.
So is okay, but do you agree with the force?
We were in a bit of a contradiction because I thought that since C and X are stored in registers, you don't need to do these data memory accesses, where as in
Right,
C,
so
you have to use the array.
right, that's the hint that I gave you, right? But how about a table?
The table it'd have to be stored in memory, I'm pretty sure.
Right, so in this way, do you think C and B, which one would have more data memory accesses?
I'm pretty sure it's C. C would have more data memory
Right,
access.
so this one is not true because we have to additionally access the table,
Yeah.
right? And this one is actually Okay, so here's the interesting thing, right? So if we don't have cache in our processor, do you think C will work?
Probably not, because then we have too much of a memory access delay or latency.
Right, exactly, right. So the trick here is that if you are running on a processor without cache, unfortunately, every processor right now has a cache, right? So if you are having a processor without cache, then this kind of table lookup optimization or any table-based mechanism would not work well because data memory access is just way too slow, right? But what really makes this idea works is just because if you look at the code, and C, the first one is correct because you only need one load and one shift, and this shift is about like one add, one shift, right? So this shift is basically replacing this 4 shifts, right? So you have a significant fewer amount of dynamic instruction count in B, right? So how about 2 and 3?
Oh, sorry. For two, the branch misprediction should be about the same because of the while X loop. So it'll constantly.
They all based on 4 iterations, 4 combined iterations, right?
Yeah. So
And they have the same amount of branch instructions, right?
yes.
All right, great answer. So for this question, most of you got it right. The answer is B. Only the first statement is correct. And in fact, C is going to give you more data memory accesses. However, it's still faster because we have cache. So it's kind of interesting, right? If one day I have a question like, give me an example of of a case that where if we well, give me a case that if I don't have cache, it won't work. Then this is a very good idea. Okay, so Joshua, what kind of question do you have?
Hi, Professor. I was just wondering, if a table is small enough, is there any kind of optimizations that can be done at like the compiler level where that stuff could actually be stored in registers if it were small enough to fit?
Well, so it's kind of interesting, right? So the answer is okay. So first of all, right, this table because it's declared as a variable, so in the very beginning you still need to allocate address for it, and you still need to allocate you still have to allocate memory locations for it, and later on you may be your compiler optimization may be using load store instruction to load all the context from the table to a certain registers. However, for this question, I don't see. Well, it's possible, but the issue is that how can you map this sequential location in a table to different registers, right? So, and it's very hard to find consecutive registers that they are all free. So, and the other thing is that if you look at the table size is 16, and for S86, we have just a total of 16 registers. So it's almost impossible in general that we can make this table fit in a register. Does that answer your question? Okay.
Yep, thank you.
Okay. So now, okay. Okay. So now, I think we are all set on this one. And now the second question is that why D is better than C? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, we definitely need some kind of group discussion. So let's go ahead, do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's look at what do you guys think after discussion. And now, well, so looks like it's either B or C, and some of you think it's D. So now, let's invite a group to talk about this. Well, how come? It's also Baylor. Okay, so Baylor, you got the first priority to talk about this. Okay, so Joe, what do you think?
Post discussion, my group had settled on the answer that B is right on the. Oh, that B is on the right one. D has significantly lower branch misprediction rate than C.
Mm-hmm. How come?
Okay, for the reasons, D has for the they have the okay, D has lower dynamic instruction count than C. So for this one, we found out that D does not have the lower. I mean, we postulated at least that we guessed that D actually has a had as D and C, they have the almost the same miss rate, and I mean the same dynamic instruction count, and two, D has significantly lower branch. D has a significantly lower branch misprediction rate than C. Was the answer that we chose that was the answer that we think is correct, and
But why?
actually I don't
But
remember the
why?
reason.
Okay.
Daniel, if you're there, please can you explain, man?
Okay, Daniel, you are called up. You might
Oh my
think,
God.
don't call me up, right?
Oh
But
no.
you got called up.
Oh,
Daniel, okay, he said he has no mic.
can you at least phone a friend?
Phone a friend. Okay, so
And
Valors, anyone, you are Joe and Daniel are definitely not the only ones who are in discussion, right? Can somebody help them? Otherwise, we will call other groups.
good Lord.
All right, other groups, what do you guys think? But thanks, Joe. Other groups who would like to raise your hand? Come on. All groups, open to all groups. This question is very interesting. I just want to let you know, and you guys will be surprised about the final answer. Okay, Joshua.
Okay. I'll give it a shot. I'm not super confident, but so
That's
I think
okay.
because of the way the for loop is treated and the compiler can unroll it, I actually think D can have a higher dynamic instruction count. So I don't think one is true.
Higher dynamic instruction count. So here's the thing. What's the definition of dynamic instruction count?
My understanding is that dynamic instructions are the number of actually executed instructions.
Right.
So if your loop is unrolled, then you would execute a lot more instructions compared to something that's looping and jumping
okay,
around.
so let's keep this on hold, right? But let's say if your loop is on hold, how does that affect 2, 3, and 4?
If your loop is on hold.
Unrolled.
Oh, unrolled. Okay. If it's unrolled, then you'll definitely have lower branch misprediction because, or you'll have lower branch instructions because you're branching less, right? If I unroll it by a factor of 4, I'll have 1/4 as many branch instructions.
Mm-hmm.
And then for lower branch misprediction rate, I don't know if the rate would be lower, but I know the number of times like whole in total would be lower that we actually mispredict.
Okay, so you just mentioned one thing that's really good called loop unrolling, right? So if we have, so tell me about the concept of loop unrolling.
So the idea is that, let's say I have a for loop that goes through something 16 times. The compiler can say, well, I could actually just paste the code in the loop 4 times, and then instead of iterating by 1, I could iterate by 4.
So why can we not doing that here?
In the while loop, I think it's because the compiler can't determine like the range across which it's going.
Right, because your X can exit at any time, right? But if your loop looks like this, the compiler can tell this is a constant. So I know this loop is going to be executed for 16 times for sure, right? So if I know this is going to be executed in 16 times for sure, as you said, we are going to copy paste this iteration for 16 times. So this is actually the resulting code, right? So if this is the resulting code, is there any branch in it?
Nope. Yeah, if you wanted to fully unroll it, you could just have all 16 operations in line.
Right, and you don't have the counter for, you don't need the counter for I, right? Mm-hmm. You don't need the branch instruction at all, right? So do you think the dynamic instruction would be necessarily lower than C?
No, I would think it'd be higher, right? Because we're executing more instructions.
Well, no, are we executing more instruction? Thinking about this, right? So for C, you have the loop, you have this one to tell, right? But now you don't have the branch at all, right? So you may not have more dynamic instructions. So I would say the dynamic instruction may be about the same, but to be honest, I don't know the answer either. So let's just run these pieces of a code on a real machine with perf and see what we will figure out. So for this pop count, right? So let's have, again, our good friend perf state and pop count. Let's say like for C, ooh, okay. So it would take a while, it would take a while, it would take a while. First of all, right, the total number of instruction that will be about, this is what? This is kilo, this is million, this is a trillion. Okay, 117 trillion. And the branch miss rate is about 0.47. And for D, let's look at that. Okay, so for D, the branch miss rate is 0 because we don't actually have branches, right? And the amount of instructions, as you can tell here, is actually fewer because you eliminate. So if you look at this, right here, we have 17 trillion branch instructions, but here we actually have almost no. We have significantly lower number of branches comparing with this one, right? So you eliminate all the branches. So the amount of branches in your code is actually a lot. So this gives you an idea that, well, it looks like the right-hand side code, we have to iterate over all 16 iterations. However, but the amount of branch instruction would definitely, compensate that. So, and another thing that some of you might be interested about that, how this code is actually compiled. So let me use this one. So I can show you the assembly code. So dash D because this is version D, right? And we have dash 03 and we have pop count .cpp. So this should be G++. See if we can learn something. So with this, you can we will generate the assembly code for the pop count. And let me see, main function, and this is the main function, and as you can tell from the assembly code, right? This is the starting of your unrolled loop. And as you can see, it's just a set of like move instructions, shift instructions, and instructions, and there's totally no branch in it, right? So that's another evidence that the whole pieces of a code get unrolled, right? So that's so you can see that after unrolled. But a more high level view of the code that I am having for you, right? This is just the high level view of the code. So with the high level perspective, as you can tell, is that, well, although it looks like the loop get unrolled and we are going to have more instructions to execute, but each 4 iterations have the branch instructions, and they are a lot. So the dynamic instruction on D is actually lower because we eliminate all the branches. And because there's no branch, so the misprediction rate is significantly lower because there's no branch, so the misprediction rate is 0. And the significantly fewer branch instructions, and that also give us the result that lower dynamic instruction count. And the amount of data memory access is actually more because there is a chance that C could skip some of the table access, but we always have to go through the 16. However, if you look at all the stuff and the demo that I show you, 3 of them are correct. So a lot of you thinking about that, well, being a good programmer, I should use the condition like the left-hand side so that I can exit the loop earlier, I can reduce the amount of dynamic instructions, but that's the case that you don't have the compiler optimization called loop unrolling. However, if you have loop unrolling involved, then the right-hand side is basically better because it would enable the chance of loop unrolling. And there's no chance for us to do loop unrolling for the left-hand side to take advantage of this top 3 reasons we have. So for the right answer for this question is actually D. And I think Tim, Mystics and Joshua, your group's answers are perfect. So for this question, surprising, that's why I'm saying like this question is very interesting because the answer is actually 1, 2, 3, and it's not very intuitive for a programmer to think that the right-hand side is better than the left-hand side. But if you know the architectural optimization and the compiler optimization that we may apply on D, then D is definitely a better option than C. So sometimes if you can predict how many times I can execute a loop, I need to execute a loop, maybe put a constant here, would that your compiler easier to get things done, right? So that's another thing. Sometimes you think there is compiler optimization, but compiler is very limited unless the compiler knows that doing this won't hurt the correctness of your code. All right, so finally, I want to give you another demo is that, well, because you might think, oh, Professor, you are presenting me a very special case. But as I said, pop count is a frequently used operation. And turns out that in SSE 4.2 instruction set extension, we have a special instruction code pop count U64. So this is so frequent. This is so frequently used in a way that the hardware has to make an instruction just for it. So that I just want to give you a quick demo. So regarding how much time it takes to execute with hardware acceleration. So without hardware acceleration, the best version we have is pop count _D, and it takes about 5.5 seconds on this. This is an AMD machine. So if I use the SSE 4.2 extension, then look at that. It's only 2.2 seconds. So it's a lot faster, right? So sometimes, well, the best programmer would think about how can I optimize my algorithm in a way that, or even though you have architecture, you have somewhat of architecture knowledge, this is the best code. This is the best code you can write, right? However, even the compiler doesn't know that you can use this kind of specialized instructions because the compiler doesn't know that the purpose of this pieces of a code is to do pop count. So as a programmer, sometimes if you really want to do performance programming, then it's really important that you have to know what's the underlying architecture of your machine, and you have to specifically use this right instructions to perform the test that you want to do, right? And it will give you a lot of performance gain in this way. Okay, so this is the hardware accelerated version of pop count. So this is probably the fastest version that you can ever come up with. And there's nothing that you really need to know about algorithm here. It's mostly just because the hardware supported. So let's just use it. All right, so now we have finished the discussion of branch, and hopefully you will feel that, wow, the branch does have a significant impact on my code. And sometimes it's a good idea that when you store data, you should have sorted it so that when you query, when you do something, the performance will be a lot better. Sometimes you should think about, like, when I write a loop, instead of thinking about how to reduce the amount of iterations, maybe I can have I can describe a fixed amount of iterations so that the compiler optimization can potentially use loop unrolling to help improving performance. Now, let's move on to the next topic that's also important in our processor design, data hazards. So we talk about data hazard as the output of an instruction is the input of a later instruction, and that result is not yet available for the later instruction to use to produce the right result. That's data hazard. So the first part of the statement, the output of an instruction is the input of a later instruction, is actually a definition of data dependency. So you can see that there are some correlation between data dependency and data hazards. So here I want to invite you, or say I want to know if you are really knowing the idea of data dependency. But before we start, I know you guys are probably very innocent about the RISC-V instruction set architecture, or sometimes, or even though I assigned the reading to you guys, but you guys never pay attention to it. So that gives you some idea about what the later instruction sets, the later sets of instruction that I am giving you is about. So so in a following problem question, I will give you a code for vector scaling. So what do we mean by vector scaling is that we add a scale to each element in a vector. So it's basically pulling all the elements within a vector, and a vector is stored as a table, or say an array in your memory, and it's a loop, and it finishes depending on the size of your vector. So if you want to rewrite it if you want to translate it as an assembly code in RISC-V instruction set architecture, this is what it looks like. So first of all, we have the shift left instruction to calculate the ending address of your loop traversal, and we have we shift left. So this X11 is the size of your array, and this X5 is actually the scaled size. So if you have double number, then this is X5 is actually size times 8. And this is the base address of your vector. So then in every loop iteration, you will load the vector and put a value in S6. And then you add S6 with X12, which is the scale vector. So the X7 is the result value. And finally, you store the value in the vector I, and add 8 to your address, which means that you are advanced to the next element. And we check if the next element is out of bound or not. So that's what the pieces of code is doing. All right. So now I have now the question that I'm asking you is that for this pieces of a code, how many pairs of data dependencies are there? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. time is up. Okay, so right now I think it's let's go to have a quick group discussion because I see there is a majority of you choosing this chose the same answer. Wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, looks like about 57% of you think is C. So I want to invite a group to tell us what does your group think. Whoa, how come it's always Baylor today? Okay, you guys, today is your lucky day. Scriber of Baylor's. Come on. Or Baylor's. Okay, Joe, showtime.
Yeah, okay. Our group, I'm not really, our group was kind of divided on the answer here, but I think
But
in
just
the end,
tell us about what you guys think.
okay. So our group had the consensus between E and D, and I personally, I'd like to think that the answer is E2. So I'm going to try and give it a shot.
So how many of them are data dependencies?
Okay, so I
how
think,
many pairs of data dependencies?
Okay, so from the limited knowledge that I have, X6 in load and add, I believe those two are the data dependencies. Okay, then X7 in add and store. I don't know if that's store double. I think that's store double. Okay. Then add integer. I'm not really sure about the add integer and branch not equal part. I think that is also there. X10. And
that's 3.
That's 3. Okay, wait. Okay, and I think between load double and maybe branch not equal, maybe this one, X10. Could it be? Pretty sure. On the
So
spot.
what's the definition of data dependency?
Okay, I'm guessing that's not it. Data dependency means that the CPU is, two threads are, two instructions are using the same data before,
So
before
for
writing it
every
back.
two instructions using the same data, should they have data dependency, or there is a criteria of that?
Oh, there's a criteria for. Wait, I don't understand. Could you repeat that part again?
So are every two instructions that shares the same register would have data dependency, or there is a bit more criteria than that?
Um,
Look at this. What we said here.
The out an instruction currently data dependency. The output of an instruction is the input of a later
So
instruction. One
output
them
of an
has to be a write.
instruction is the input
No, wait,
of a later instruction, right?
Yeah. So it.
So
it has to
if you
be-
look at that, what would be the answer you put now?
I think it's gotta be C. I think.
Right, because only the three fulfill this requirement, right? So thanks,
Yeah.
Joe. Thanks for Valers, right? So for this question, the answer is actually C, because only these three pairs, they are so-called data dependency, in a way that our definition of data dependency is that an earlier instruction is the input of a later instruction. Winston, question.
Yeah, I had a question. So, would we recently we learned about the out of order execution? Would this would the out of order execution affect how many data dependencies we would have?
Well, so out of order, so that's a very good question, but the data dependency here is in terms of if you execute this instruction in order, right? And you will learn that the additional data dependencies that in out of order execution, which you will later see, we call them false dependencies, right?
Yes.
So if it's false dependency, do you think they are real data dependencies? No.
I guess
Right,
not, because
like-
they're caused by you purposely
That
causing them to
yeah,
happen.
because you out of order than on purpose, right? So that's a different that's not true dependency. So the true data dependency we have here is only three. So now, let's look at this. If we can only stall, if our processor only knows use stall to address that, and the pipeline is actually copied from your textbook figure C.25, which you may already know about us. So for the pipeline without any data forwarding, without any optimization, whenever all it can do is that whenever we have a data dependency that we cannot address, we just need to, we can only stall. How many data dependencies, how many pairs of instructions will result in data hazard or stalls? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so here we go. It looks like we have a tie on 2 of the answers. So why don't you guys go ahead and discuss with each other? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now after discussion, I see more C's than B's. So I want to invite a group to tell us, what do you guys think? Okay, instinct. Okay, Bjorn, what do you think?
Yeah, hi, Professor. So I think for this one, we will have this add instruction. The second one will have data dependency of x6.
Mm-hmm.
The store instruction will have data dependency on the previous add instruction on for
Mm-hmm.
x7, and the branch
Mm-hmm.
instruction will have the data dependency on x10, which is
Okay, so but
calculated by.
why we have to stall, why we have data hazards?
So basically, the result of the register that we want is not present in the uh, yeah, is not present in that particular is has not been updated.
Right.
So
So here's the thing, right? If you want to know if there is going to be a data hazard or not, the best thing to do is to draw the data the pipeline diagram, right? And for the pipeline diagram, well, the first couple cycles we have no issues with that, but for the fourth cycle, right? Because the load instruction will only have XC6 getting the right value after its memory stage. So we have to wait for one cycle here, or we have to stall for one cycle here. And then, well, but before we write back, there's no way the add instruction could get the right value, right? So you have to wait for the load instruction to write back in the first cycle and first half of the cycle, and then the add instruction will be able to get it from the second half of the cycle. And thanks, Guillaume. And for the third instruction, because the add instruction is blocking on the instruction decode stage, so it will also be blocked at the instruction fetch stage. So that's why the cycles looks like this. And after the load instruction finish its write back, the add instruction can finally make progress. But the same thing would happen when we are dealing with the add and store and the add immediate and branch instruction, because for the add immediate, again, the branch instruction need this value for its decode stage, but that's not ready yet until the add immediate finish write back. So that's why you will see, if you don't have anything to address that, every data dependency in your code, it would become a data hazard. So, but in the next lecture, we are going to talk about how we can avoid some data dependencies become data hazards through better options like data forwarding or dynamic instruction execution. But before we finish the lecture, let me pull up a few things, because I think a lot of you still have the question about the midterm, and sometimes I just feel like, wow, you guys are so care your grades so much. So I think we definitely have to talk about this. So a lot of you were asking me about like this bar chart. What is this? So this is the weighted total that you can find in your iLearn. And the reason why I put weighted total instead of your midterm grades, because midterm is only an item that accounts for 25% of your grade. What really determines your overall later grade at the end of the quarter is the weighted total. And some of you are asking me why I only see like 40-ish or 30-ish in my weighted total. Is because currently we only have 50% of the grades offered so far. So the other 50%, 35% of them are coming from your final, and 15% of them are coming from your project, which is already up, and I don't see a lot of you starting working on it. And even for the 50% that has been offered, there are still 25% of that coming from your assignment. For example, assignment 4 is up, and if you really want to boost up your assignment grades, you should start early. Don't start it at the last minute. And we have reading quiz due next week, but I think I pushed the deadline a little bit because I think we are falling behind on our schedule a little bit. So the next reading quiz, I believe it will due next Wednesday. So reading quiz is also another way that can boost up your performance. And the projected grade that I put here, as I mentioned, it's based on relative ranking. So there is no so some of you might be asking like, okay, so if I got a total of 90% of my grades, will I potentially get a B plus? Well, possible if a majority of the class is more than 90% of the grade. But since I have been teaching a class starting from the 2012, it never happens. And it turns out that my curve would help you getting better grades. So trust me, right? And don't be too worried about the grades, and just try your best to learn the stuff from the class. And here is a projected later grade that I have. So far, I plan to give all of you grades above than B minus. If I don't find any cheating case, if I feel like every one of you is working hard toward the quarter, right? And trying to focus on the most important bits of things that I want to teach you, right? But if I do find there are some integrity issues among our students, I might change my mind. So here's my current planning about the grading, but it could change, right? And again, it's based on relative ranking. So if you try to help your colleague to get better grades in some way, which we call cheating, is basically hurting you because he might or she might get better grades than you at the end, and you might get worse grades in that case. And for the solution of the midterm, you can definitely go into your revisit your midterm from iLearn, and I think all the answers are there. And if you yeah, so and for those free answer questions, I will ask the TA to publish the answer at some point. And the regrading period is only 1 week, and you have to send us a written report, and the process has been listed on the website, so please go through it. Other than that, I would I hope you have a great rest of the week, and if you have any other questions, feel free to ask me through office hours. Other than that, enjoy the rest of your day, enjoy the rest of the week. I will see you later. So you just need to go through iLearn to look at your answer.